you're training a language model, and every word it says gets nitpicked. That's how most reinforcement learning works, rewarding or clipping at each token. But what if we judge the whole sentence, like a teacher grading essays instead of grammar drills? That's exactly what GSPO does. Group Sequence Policy Optimization. Instead of focusing on token-level importance ratios like GRPO, it zooms out and looks at the entire response to decide how much to trust and train on it. The result? Less noise, more stability, and no need for clunky fixes like routing replay, even in tricky mixture of experts models. This paper shows how thinking in full sentences literally leads to smoother, smarter training. Let's dive into how it works and why it might just be the upgrade large language models have been waiting for.
Let's dive into the exciting world of reinforcement learning, or RL. It's a powerhouse approach for scaling those large language models we keep hearing about. These models aren't just for chatting. They're taking on complex tasks, like high-level math and intricate programming. But there's a hitch. Current RL methods, especially those like GRPO, aren't quite cutting it. They're stumbling with stability issues when dealing with these massive models, leading to catastrophic collapses. Imagine investing all that computational power only to see it crumble. Ouch. So what's causing these hiccups? The instability is rooted in how important sampling weights are applied. As the response length increases, the training noise grows, making things even shakier. Enter Group Sequence Policy Optimization, or GSPO. This is the hero of our story, designed to fix these flaws. Its secret sauce? A new way of defining importance ratios, based on sequence likelihood. It doesn't just fix things. It makes RL training smoother and more efficient. GSPO is particularly good at handling mixture of experts models, which are notoriously tricky. This new approach simplifies the RL infrastructure, paving the way for advancements in language models, like the latest Qwen 3 models. In essence, GSPO is the stable, efficient algorithm that could redefine large-scale RL training. Let's break down some technical details now. We're diving into two key algorithms: Proximal Policy Optimization, or PO, and Group Relative Policy Optimization, known as GRPO. These are heavy hitters in the field of RL, tackling the challenge of optimizing policy updates, essentially helping improve the decision-making process of AI models. PPO uses a technique called clipping to manage policy updates, ensuring changes aren't too extreme. It relies on a value model to estimate advantages, but can be computationally demanding due to its size. This is where GRPO steps in. Unlike PO, GRPO forgoes the value model and calculates the relative advantage of each response within a group, making it more memory efficient. But why these methods? As models grow and responses get longer, complexity increases. RL often uses off-policy learning, which means using data generated from a different policy. However, this introduces challenges, especially around sampling weights. GRPO's approach of using these weights at each token position introduces noise, which can lead to instabilities. Overall, understanding GRPO and PPO is crucial for managing large-scale models. These algorithms face inherent challenges, particularly when dealing with distribution mismatches in sampling. Now, let's zoom in on the heart of our discussion: Group Sequence Policy Optimization, or GSPO, and how it shifts from token-level to sequence-level optimization. The problem with token-level importance weights, as used in methods like GRPO, is they don't align well with the unit of reward, which is granted to the entire sequence. This mismatch can lead to inefficiencies and inaccuracies. GSPO tackles this by applying importance sampling at the sequence level. It looks at how far a generated response deviates from what the model expects, providing a more holistic view. The optimization objective for GSPO involves minimizing a clipped advantage over groups of responses, ensuring a stable and efficient learning process. Let's dive into some math here. The concept of a group-based advantage estimate uses a mean and standard deviation of rewards to assess performance. There's also a sophisticated calculation for the importance ratio based on sequence likelihood, involving an exponential function of a log sum, which helps control the variance and maintain a consistent numerical range. Finally, we derive the gradient of the GSPO objective, explaining how various components interact during optimization. This sequence-level approach in GSPO aligns with the reward system and simplifies the clipping mechanism, making it a robust framework for large-scale language model training. Next, we explore the intricate differences between GSPO and GRPO, particularly in how they handle gradients. GRPO weights the gradients of token log likelihoods based on their importance, leading to potential instability, as these weights can vary significantly. GSPO, however, treats all tokens equally, offering more stability. Then, we meet a variant called GSPO token. This version allows for more granular control by adjusting advantages at the token level, especially useful in multi-turn reinforcement learning scenarios. The objective here is similar to GSPO but focuses on token-wise customizations. The math behind GSPO token involves a numerical operation that stops the gradient, allowing flexibility without altering the underlying optimization process. This ensures that while individual tokens can be adjusted, overall learning remains stable and consistent. Finally, we segue into discussing experiments. We hint at empirical results, with a model fine-tuned from a specific base, comparing performance across several benchmarks. This sets the stage for understanding how GSPO and its variants perform in real-world scenarios, offering insights into their practical effectiveness. Now let's get into the world of empirical results. Check out Figure 1 here. It showcases how GSPO outperforms GRPO in training efficiency and accuracies. It's like watching two cars race, with GSPO consistently speeding ahead, showing better performance across various tracks like AIME24 and code forces. It's all about that stable and effective learning journey. There's an intriguing observation regarding clipping. Look at Figure 2. It reveals that GSPO clips entire responses rather than individual tokens, unlike GRPO. Despite clipping a much larger fraction of tokens, GSPO achieves higher training efficiency. It's like pruning a tree, where GSPO's approach leads to healthier growth by focusing on the bigger picture rather than individual leaves. The takeaway here? GRPO's token-level clipping can be noisy and inefficient, while GSPO's sequence-level strategy provides a clearer learning signal. Overall, this page illustrates the robustness and effectiveness of GSPO, proving that sometimes, taking a broader perspective leads to better results in the complex landscape of reinforcement learning. Let's dig into the benefits of GSPO, especially in the context of mixture of experts models. These models are tricky because they activate different parts, or experts, depending on the input. When using GRPO, this can lead to instability because the experts change frequently, throwing off the training process. Imagine trying to hit a moving target. It's challenging, and that's what's happening here. To tackle this, the authors previously used a technique called routing replay. This involves caching the experts used in past decisions and replaying them to maintain stability. Check out Figure 3 to see how this strategy helps GRPO converge properly. But there's a catch. It adds extra overhead and can limit the model's capacity. Here's where GSPO shines. It doesn't rely on routing replay. Instead, it focuses on sequence-level likelihoods, which are more stable and don't fluctuate wildly. This makes GSPO a more efficient choice, simplifying the process and allowing the model to use its resources fully. In terms of infrastructure, GSPO bridges the gap between training and inference engines. It uses sequence-level probabilities, making it more resilient to precision discrepancies. This adaptability is especially useful in flexible setups, like partial rollout or multi-turn reinforcement learning. Thanks for joining us today. Happy exploring together!